This is the key to Sage and Scribe gas loss problems set 2. So let's go and start with number 1. In number 1, we're starting off with a sample of nitrogen gas is cooled from T1 to T2. Final volume, V2. What is its original volume, V1? So if you look at this equation, or all the variables that are changing, it looks like we're going into Charles' law, which is V1, unknown to us, over T1, which is 1200 degrees Celsius, but we have to convert that to Kelvin, giving us 1473 Kelvin units, equaling V2 is 2.5 liters, and of course the 25 degrees Celsius, which is our T2, adding 273 is 298 Kelvin. I like to solve this problem by doing the butterfly method or cross multiplication, and you get your final answer, which is 12.4 liters when you multiply and divide what you need to do. So now let's look at the next, number 2. In number 2, a submarine has a volume, so here's my V1, and a pressure, here's my P1, and my temperature of 15 degrees, which is my T1. This submarine descends to a depth of 150 atm, which is my P2, at a temperature of 3 degrees Celsius, which is my T2. It's asking for my V2. So it looks like I'm combining a lot of variables, V, T, and P. Those are all changing variables. So it looks like I'm using the combined gas law. So P1, as stated, is 1.0 atm. V1 is 1.2 times 10 to the fifth liters. V1 or T1 is 15 degrees Celsius, adding 273 to it is 288 Kelvin. P2 is 150 atm. V2 is what we're looking for. And then T2 is 3 degrees Celsius, adding 273 to that is 276 Kelvin. Once again, do your cross multiplication and division. You should get your final answer of 770 liters of the gas inside the hull once the submarine goes to that depth of 150 atm. So now let's look at the next problem. The next problem, in number 3, I can kind of guess it's a stoichiometry problem, and I can see it because I see a balance equation, and you're given 75.0 liters of chlorine, and you're asked to find grams of hydrogen. So it's asking me to really connect these two through this balance equation. Notice that chlorine and hydrogen have a 1-to-1 mole ratio. So let's go ahead and take our given, 75 liters of chlorine. It's a diatomic molecule. And I'm going to convert it to hydrogen. Now, how would I do that if I have liters? Well, as long as we're at constant temperature and pressure, and we're at that when we're at STP, we can then assume that the volume will be just like the mole ratio between the two. So between chlorine and hydrogen, we said that the mole ratio is a 1-to-1 mole ratio. And we can see that in the balance equation. For every 1 chlorine gas, there's 1 hydrogen gas. So they're proportionally the same in terms of mole ratio as well as liter ratioing here. So then I go to the next converter because I'm not quite at my grams of hydrogen yet. I've got to get liters out of the way, and I've got to get to moles to get to grams. And so that's why I know I'm going to use molar volume. Now at STP, I know that 1 mole of any gas has 22.4 liters of that gas. So this is only at STP conditions that this is the case. And then I'm going to do my last step, which is taking my moles of hydrogen and converting it to grams. And you look at that up on the periodic table and you see that there's 2.02 grams per 1 mole. So doing all the math, you then will see your final answer to be 6.76 grams of hydrogen. Now, be aware that in cross-canceling your dimensional analysis units, you can see how it all works out nicely. So liters of chlorine cross-cancels, liters of hydrogen cross-cancels, moles of hydrogen cross-cancels, leaving us with grams of hydrogen, which is ultimately what we're trying to solve for in the end. Moving on to the next problem. In the next problem, you're looking at moles being given to you, volume being given to you, temperature being given to you, and pressure. So which equation utilizes all 4 of these variables, one of which you're going to have to solve for, and that is the ideal gas law. So let's go ahead and use PV equals nRT. P is 20,300 kPa. V is 30 liters. N is what we're solving for. Now when you choose your R, you look to see what your pressure is in. Pressure is in kPa. So the R of choice will be, looking at your notes, the R of choice is 8.314. And that is in liters times kPa unit-wise. So I'm going to put all the units so you can see how the units work out. And of course, temperature, it looks like it has to be in Kelvin, as you see here, just like volume has to be in liters. N is going to be in moles. Your temperature has to be in Kelvin. So adding 2, and it is in Kelvin. So 300 Kelvin is our temperature. So solving for N and working out its units, you will get 244 moles. I'll rewrite it here as well, of your gas. Now notice how the units cancel out. kPa on top on this both sides of the equation, so they cancel out. Liters on top on both sides of the equation. Kelvin on top and bottom of the fraction, so they cross cancel, leaving us with moles as our final unit in the end.